The inverse operation of raising something to a power is called taking the logarithm, or often just taking the log for short. So with logarithms, we need to specify something. We need to specify what is the number that we've been raising to a power, so we know what to talk about when we're going backwards through that process. So for example, we had 2 to the power of 3 is 8. 2 times 2 times 2 is equal to 8. Then the logarithm to the base 2 of 8 is 3. It's the power to which we have to raise 2 in order to get 8. So we can generalize here. If we take a chain of n numbers, g, multiplied together, then g times g all together n times n different g's here, then we would call that, of course, g to the n. Then n is the log to the base g of g to the power n. That is, n is the power to which we have to raise the number g to get the answer g to the power n. Now, so far we've just talked about raising numbers to integer powers, and the same thing has been true so far of our discussion of logarithms and working backwards from that. But we can actually generalize to non-integers. We don't have to restrict these powers to just being integers, n. So, suppose we've got some number b, then saying that a is equal to log to the base g of b means that g to the a is equal to b. One important restriction here is that we can only take logarithms of positive non-zero numbers. The log of 0 is not defined, and the log of negative numbers we can't define using our real numbers here. Now, of course, if we are multiplying 2 to the power 2 by 2 to the power 3, we could write it out here for the integers. That would give us 32, but it would also be 2 to the power 5. It doesn't matter with the parentheses whether we leave them in multiplications. So we see that multiplying 2 to the power 2 by 2 to the power 3 gives us 2 to the power 2 plus 3, which of course is 2 to the power 5. So in multiplying here, we have added the exponents. Generalizing to non-integers now, we can generalize and say g to the power a times g to the power b is g to the power a plus b. So if we write that some number capital A is equal to g to the power small a, that means that log to the base g of a, capital A, is equal to small a. And if capital B is equal to g to the power small b, then log to the base g of capital B is equal to small b. Then the log to the base g of this product, a times b, is log to the base g of g to the power a, because a is just g to the power little a, times g to the power little b, because uppercase B is just g to the power little b. And we know since g to the power a times g to the power b is equal to g to the power a plus b, then what we have in here must be what we have over in these parentheses. And we know by definition that log to the base g of g to the power a plus b is just equal to a plus b. But that is equal to the log to the base g of capital A plus the log to the base g of capital B. So multiplying numbers is equivalent to adding their logarithms. And that was one of the main reasons why logarithms were used to do calculations for many years. If you had log tables, you merely had to do additions in order to multiply numbers. When we use logarithms for ordinary calculations, we typically use logarithms to the base 10. Base 10 logarithms are very often used by engineers in expressing power ratios. So though we don't really need to do logarithm-based calculations anymore for the sake of doing real numerical analysis, we do use them quite a lot because the logarithms to the base 10 are very convenient when we are talking about amplifiers and losses in communication channels and things like that. And in practice, we use a unit called decibels, abbreviated to small d and capital B. And the decibels are 10 times the logarithm to the base 10 of the power ratio. So, for example, suppose we had an amplifier whose output power, P out, is 100 times larger than its input power, P in. The gain in decibels would be expressed as 10 times the logarithm to the base 10 of the gain of the amplifier, the output power divided by the input power. So, since the output power divided by the input power is 100, and log to the base 10 of 100 is simply 2, because 10 squared is 100, then our gain in decibels here is 10 times log to the base 10 of 100, which is 10 times 2, which is 20 decibels. So another good example would be an amplifier with a gain of 2, noting that log to the base 10 of 2 is approximately equal to 0.301. Then a gain of times 2 in decibels is 10 log to the base 10 of 2, which is approximately equal to 3 decibels. Most engineers will use the idea of 3 decibels as another way of expressing a factor of 2. As I said, although we don't really need to use logarithms to do calculations anymore, it turns out to be very convenient to have decibels to work with as units when we're analyzing things like amplifier chains, because if we have various different amplifiers and various different loss factors as we go through some cable or the like, we simply add the decibels up to understand the overall gain or loss through the system. Of course, losses, which would be ratios of number that are smaller than 1, give us negative numbers of decibels when we take the logarithm. So logarithms of numbers less than 1 are negative numbers. Now, it turns out to be quite useful and important to be able to change the bases of the logarithms that we're working with. So, for example, suppose that log to the base 10 of some number b is a. Could we figure out how to write this as a log to the base 2, for example, instead? So, the fact that log to the base 10 of b is equal to a means that b is equal to 10 to the power a. Now, by definition, 10 is just 2 to the power of log to the base 2 of 10. That's what log to the base 2 of 10 means. So, our number b here, which is 10 to the power a, is 2 to the power log to the base 2 of 10 to the power a. And we know that if we are raising a power to a power, we just multiply the two of them. So b is equal to 2 to the power log to the base 2 of 10 times a. So log to the base 2 of b, which we can do here, we know b and we've got it expressed as a power of 2, is therefore just this exponent here. That is, it's log to the base 2 of 10 times a. But a, we figured out a long time ago by definition up the top, is just log to the base 10 of b. So log to the base 2 of b is log to the base 2 of 10 times log to the base 10 of b. We can generalize this and drop the parentheses here with the logs and the multiplication sign and say that log to the base c of b is log to the base c of d times log to the base d of b. Notice that the d's here are the same number in the two different positions in the middle of this expression here, so it makes it kind of easy to remember. Log to the base c of b is log to the base c of d times log to the base d of b. When we're talking about logarithms, sometimes the loose notation is that the logarithm, written just as log, means log to the base 10. For example, that's often the case on a calculator keyboard. This is not a very reliable notation, however. Another common base of logarithms is logarithms to the base 2, which we've already looked at. We would write those as logs to the base 2 here. And they're important because we use binary numbers quite a lot, for example, in computer science. Fundamental physical science and mathematics, however, almost always use logarithms to the base e, where e is this rather strange and irrational number here. It goes on and on and on. It's about 2.718. And it's called the base of the natural logarithms. And why we want to work with logarithms to that base will become clearer as we go further on. The mathematics becomes particularly elegant if we work with logarithms to the base e. Let's look at some notations associated with the use of this number, e, the base of the natural logarithms. So logarithms to the base e are called natural logarithms. And we could write them like this. That's perfectly correct, and that notation is used. Sometimes also we may see people just using the notation log. An unambiguous and short notation is this notation here, which is ln. So the letter L here we can think of as being logarithm, and the letter n as being associated with natural. So natural logarithms use the notation ln. Now, this number e, of course, is a mathematical number, but the letter e in physics is often used to represent the charge on an electron, and we don't want to get confused. Also, since we will very often be taking exponents of the number e, we want to avoid having superscript characters all over the place. So to avoid using the letter e and to avoid these superscript characters, instead of writing e to the x, which is still perfectly legal and perfectly all right, we will try instead to use this notation here, exp of x, or the exponential function, e to the x, exactly equivalent to this notation here, exp brackets with x in the middle. Let's just have a look at these functions. Here's what the exponential function looks like, or e to the x. You can see that as we go to larger negative arguments, it gets closer and closer to the horizontal axis. It is called, therefore, a function that asymptotes to the x-axis. And for larger positive arguments, it grows faster and faster and faster. The logarithm, the inverse operation of that, is a function that grows rather slowly in the forward direction. The logarithm of 1 is 0, and as we go below the number 1, taking logarithms of numbers smaller than 1, the logarithm function becomes larger and larger and larger in negative numbers, and it gets infinitely large as we get arbitrarily close to 0 with the x. So for smaller positive arguments, it becomes arbitrarily large and negative. So let's just look at some formulas which turn out to be very useful in manipulating exponentials and logarithms, and all of these can be deduced from the discussions that we've had above. First of all, the product of two exponentials is just the exponential of the sum of these arguments. The log of the product of two numbers, the natural log, is, like for any other logarithm, the sum of the logs of each of the numbers. 1 over exp of a, 1 over e to the x, is, of course, e to the minus x, or exponential minus a. The log of 1 over a number is minus the log of the number, because this is a number to a negative power. That's where the minus sign really comes from. And this is true for all logarithms, not just the natural ones. The exponential of the natural logarithm of a is, of course, just a. And the logarithm of the exponential of a is also just a.